Welcome to this video. Thanks for listening, and many thanks to the organizers as well for organizing this online conference. And the topic that I'd like to discuss is the role of isocurvature modes during turns in inflation and their imprint on the CMB. So just to get started, I'm sure most of us will be aware that the CMB data is perfectly compatible with a number of key inflationary predictions, including an almost scale invariant power spectrum. And the 2025 value for the spectral index, for instance, based on this data, is this particular value. Now, this is perfectly compatible, these findings, with single field slow roll inflationary models. And next goals would be tensor modes and also very much non-Gaussianities. And of course, the latter would offer an excellent avenue to see the imprint of additional fields, which we would expect from a UV perspective. So that's what we'll be looking at in this particular video. We're thinking about multi-field models. In particular, we'll focus on the multi-field effective field theory for fluctuations. So we'll consider that the background has been taken care of. The background will be taken to be very close to the sitter, and we're assuming very negligible time variation. So we'll have a sustained period. Then the linear physics, in the case of two fields, there's two fluctuations, there's curvature and there's isocurvature, zeta and sigma, and the linear physics is described by the following effective field theory. This is the kinetic term for curvature fluctuations that can be a mass term due to their Goldstone nature. There's isocurvature, kinetic term, and a mass term. And finally, and very importantly, there can be a mixing between curvature zeta and isocurvature sigma. And that's described by this turn rate eta perp. Eta perp is important because it turns out that due to the mixing induced by this mixing term, there's actually a term that sources the evolution of isocurvature fluctuations and basically shifts the mass term away from the bare mass, m sigma squared, to an effective mass. And the size of this shift is set by the turn rate and is given by 4 eta perp squared. So this shift allows for the interesting possibility that the isocurvature modes by themselves are unstable. Sub-horizon evolution will be unstable, but due to the shift, actually super-horizon, they'll be stable. M sigma effective squared can be taken positive. And this is a regime which happens in many, many different cases, different inflationary models, including geometric destabilization, hyperinflation, hypernatural inflation, angular inflation, etc. And is generically referred to as slow roll, fast turn. We'll consider exactly this case, and moreover, for simplicity, we'll take the effective and bare mass to be exactly opposite. And we'll use the parameter x to indicate the value of the masses in Hubble units. So x is a dimensionless quantity. And due to this instability, there's an interesting evolution for every mode, because they start out in the Bunch-Davis vacuum. At some point, they'll start evolving, they'll become unstable, up to the moment when they cross the horizon, because their super horizon evolution is governed by the positive mass. So again, they're stable. So there's a transient instability for these particular modes. And it'll be interesting to distinguish the heavy, x larger than 3/2, light smaller than 3/2, and massless, equal to 0 cases separately. And what we'll be doing is we'll be evolving these modes under the linear behavior, and we'll be inserting a number of nonlinear operators to generate bispectra. And the 3 cubic operators that we'll be discussing are the 3 given over there. And indeed, we'll look at the resulting bispectra, and we'll do the heavy and light cases with Cosmoflow, and for the massless case, we'll use PyTransport instead. Okay, let's get started with the first case, the heavy case. So what have we got here? Here we're showing the bispectrum for a given operator at a given mass value, an example of the heavy case. And this is all based on a paper together with Shuntaro Aoki, as well as Dennis Wert and myself, that will either appear soon or maybe has already appeared soon by the moment that you're watching this video. So this is the bispectrum for the different momentum configuration, the different triangles, and what's important to highlight. So for one thing, when you go to the squeeze limit, which is over here, the bispectrum vanishes. And that's perfectly natural, exactly what you would expect based on the Maleshenes soft consistency relation. Secondly, we've normalized our bispectra to be equal to 1 in the equilateral limit, which is over here. And you can clearly see from this template that the moment you move away from equilateral, the bispectrum always goes up. So wherever you go in momentum space, the bispectrum will always be larger, and indeed there's a peak in this fully folded limit, and also there's a peak at this mildly squeezed limit, in between the 1 in equilateral and the 0 in fully squeezed. And this peak happens at a particular momentum ratio that we understand. And here the peak may not be very pronounced or impressive, but as you crank up x, this peak actually goes up as well. Interesting. Oh, sorry. So this was for one particular operator. Let's also have a look at other operators. So here we're looking at the 3 different operators, different color coding, for purely isosceles bispectra. So not the full template for all possible triangles, but only isosceles triangles. The gray line over here is equilateral. This is the folded, and this is the squeezed limit. So again, we start out at 1. You'll see that if you go towards squeezed, the 3 different operators basically have the same behavior, very, very, very similar. And instead, if you go towards folded, there's growth for all operators, but some grow much faster than others. Interestingly, there's a fun comparison to be had with a single field approximation done by Sébastien already a number of years ago, where they took the same model and they wrote down a single field EFT approximation, which you obtain by integrating out the heavy mode, the isocurvature mode, and then you're left, of course, with only curvature, and the remnant of the transient instability is the fact that these have a negative speed of sound squared. Now, comparing the single field approximation with the exact multi-field result, we find, first of all, that they expect that the single field captures the features correctly. So indeed, they find a peak as well, and they find this peak over here in mildly squeezed, and they find this peak here for folded. The amount of features are too large, or overestimated by a magnitude, which we describe in our paper, which is related to 1 over x. We think there's a very nice physical explanation why this particular single field overestimates the bispectrum, and that's related to this picture that we had before, where every mode starts off in Bunch-Davies and then experiences this transient instability and subsequently freezes out on super horizon scales. Now, what the single field EFT does is it basically sets a cutoff at the moment when the shortest mode just enters or starts evolving, basically. So it doesn't take into account this period before that. So that means that it'll miss part of the evolution of both modes K1 and K2, and of course misses most from the longest mode K1. Now, it turns out that the bispectrum will not get contributions from 3 modes that are all 3 growing, and in fact, the leading contribution will be the growing, decaying mode. So then the question is, which of those modes will be growing, and which 2 will be growing, and which 1 will be decaying? And since you're neglecting this part, your best bet, the largest contribution, will come from the case where K1 will be decaying and K2 and K3 will be growing. Because then you're missing part of the decay, and hence your contribution will be largest. And indeed, we think that this is why the single field EFT overestimates the bispectrum, because it's neglecting part of the decay of the longest mode. Okay, continuing on to the next case, that's the light case. So what's happening here? Again, we're plotting the bispectrum for a given operator at a given light value, x equals to 1. Now, let's see. In contrast to the heavy case, in the light case, in the fully squeezed limit, it doesn't go to 0, but actually it peaks with a specific power law, and you can perfectly understand this because this is a result of the Cosmo Collider signal, which was, of course, already discussed at length before. So we find that away from the squeeze limit, again, we normalize to be exactly 1 in equilateral, and whatever direction you go into, again, you're finding that the bispectrum increases away from equilateral. And that's not just true for this particular operator, it's true for the other 2 operators as well. Here again, we're showing 3 different operators in 3 different colors, and you're seeing that away from equilateral towards squeeze, they start peaking and nicely conform to the Cosmo Collider signal with a specific power law behavior, which is given over there. And towards folded, again, we see growth for all operators. The rate of growth is very different for different operators. All right, now let's apply this to a particular model, and the model that we'll be comparing to is angular inflation. So what's angular inflation? Well, angular inflation consists of a specific hyperbolic scalar manifold. So the kinetic term is given over there. This is a hyperbolic manifold whose curvature is set by alpha, and we're just augmenting this with the simplest possible potential, quadratic potential, with two quadratic masses for the two fields. Now, it turns out that if you go to the limit where both the curvature and the mass ratio between the two masses is large, that the model or the fields do not display single field slow roll, but instead there's a new dynamical attractor, which we dubbed the angular phase, and you can see it in action over here, where we show the behavior for different initial conditions of what the background fields are doing, and you're seeing that they're all going to conform to this nice specific new phase, the angular phase, which turns out to be slow roll, fast turn. And here the black dot is CMB horizon crossing, and then you're doing 50-60 e-folds afterwards. Okay, so what does this model look like in terms of bispectra? Well, that's something that we've calculated. So it turns out indeed to fall in the class that we're considering. It conforms to this transient instability. In particular, it's x roughly equals to 1. And we also check the amount of non-Gaussianity, so it's larger than single field slow roll by a bit, not by much, but by a bit. So FNL is order minus 0.2. And the shape of the bispectrum is interesting because it's roughly flat when you move away from equilateral towards squeezed, and only at the very end does it start to peak. And instead, if you move away from equilateral to folded, it starts to go down. And actually, it peaks in a negative value in fully folded. So how can this be true? How does it compare to what we showed before, right? When the three operators all increased away from equilateral. Well, it turns out that even though the operators separately all increase, linear combinations don't have to, and indeed, angular inflation exactly corresponds to a specific linear combination of these cubic operators that I showed you before, which combine into this particular behavior of flat in this particular direction and decreasing in this other direction. Okay, only one more case to go, which is the massless case, x equals to 0. Now, this case really is very different from the two cases that we've discussed previously. So why is that? Well, first of all, it's the massless case. Isocurvature modes are massless as well. On top of that, because the mass and the turn rate are coupled, the turn rate also vanishes, and hence the two fluctuations are fully decoupled. So they're massless, they're decoupled, which means that there's no super horizon evolution to both curvature and isocurvature. And that means that by the end of inflation, you'll arrive at the epsilon equals to 0 point with power in both type of modes. And of course, the power in curvature modes is something that we'll be observing, but the question is, what happens to these isocurvature modes after inflation? Now, because all of the fun in this case happens after inflation, this analysis is necessarily model dependent. And so we have to pick a particular model to be able to specify what happens after inflation. And one of the models that's very interesting and suitable for this is modular inflation, which was introduced by College and Linde in 24. And again, it consists of a hyperbolic scalar manifold. In this case, we're using Poincare half plane coordinates with a dilaton and an axion. And on top of that, they're imposing a potential that realizes a discrete subgroup SL2Z of the isometry group SL2R of this particular scalar manifold. So in this sense, the motivation for modular inflation is very similar to natural inflation, which is a single field case with a shift symmetric kinetic term, d chi squared, augmented with a periodic potential that realizes a discrete shift symmetry. Here we're realizing the discrete subgroup of the SL2R isometry group of the hyperbolic manifold. And of course, these potentials are naturally formulated in terms of modular functions like the Dedekind function and the J function. And interestingly, if you ensure that you can have nice inflation along the dilaton direction phi in this direction, the orthogonal direction turns out to be very flat. The potential in chi, actually the chi dependence, is doubly exponentially suppressed. So indeed, isocurvature modes are basically massless in this direction, and you're just inflating along this particular direction. So if you're looking at specific trajectories and you let them roll in this particular scalar potential, here we give the result for two choices of initial conditions. First, you're rolling down along phi, and then at some point you start finding your minimum, and that's in order to get there, you'll have to start turning. So we're distinguishing between the solid lines, which is the inflationary phase. This is epsilon equals to 1, and afterwards, past inflation, all sorts of turning happens. Again, during inflation, motion is purely or almost perfectly geodesic, and the turn rate basically vanishes. And after inflation, instead, there's strong turns, and hence the two modes finally start mixing. Right, so what about these fluctuations? How do they behave when the background does this particular behavior? Well, here we're looking at the power spectrum, first of all, for curvature and isocurvature modes. And as I mentioned, these are roughly massless and decoupled during inflation. So indeed, we would expect zero super horizon evolution. Here we're showing the power spectrum for a given wavelength, for a given momentum value. And indeed, you see that they're roughly constant. The orange one is isocurvature. It varies a bit due to slow roll corrections, but they're roughly constant. During inflation, instead, after inflation, everything happens, all hell breaks loose because of the turning towards the minimum. So what happens to the powers in both curvature and isocurvature? Well, orange, again, is isocurvature, and you see that very, very quickly decays. So you turn out to have a very quick and efficient transfer of power from isocurvature, which decays very quickly, into curvature. And indeed, curvature power spectrum can go up, in this case, by 2 orders of magnitude. So you can really result in a significant increase in the curvature, in the power in curvature. So this is really something you want to take into account, because this is, of course, what we'll be measuring in the end in the CMB. Now, this is it for power. We've started a analysis with a number of people in Groningen. But it's very much prelim. But just to give you a taste, for the non-Gaussianities, we're seeing a very similar enhancement. So again, during inflation, it's roughly constant. Of course, at slow roll suppressed values, roughly 10 to the minus 2. And afterwards, during a couple of e-folds, it can spike up and take a new value, and it's constant from that moment onwards. And it can really increase gain power, which is a couple of orders of magnitude, just such that it becomes either observable or even ruled out, depending on the initial conditions. So this is a very clear signal that this is not single field, but very much multi-field behavior. Okay, that brings me to the end of my talk. Let me wrap up with conclusions, hopefully within 20 minutes. So we've discussed the role of isocurvature modes during inflation, looked at their bispectra, and we focused on the case where we have these transient instabilities because of the clear multi-field signatures that the bispectra offer. We've seen that the 3 different cubic operators that we've introduced, that we've discussed, all lead to similar effects. In particular, the bispectrum increases when you move away from equilateral, and for the heavy case, it results in this resonant peak that we discussed at a particular ratio of long and short mode. And we compared this to the single field EFT. And in the light case, instead away from equilateral, it starts to increase all the way to the squeezed case with the cosmological collider signal. And we compared this, or applied this formalism, to the angular inflation case. And finally, the massless case was really very different, because there all the fun, in some sense, happens after inflation. The previous 2 cases are all, in some sense, more universal, because everything happens during inflation. Here it's really dependent on how you find your minimum. And we've shown in a particular case, modular inflation, how this happens, and in particular, how the isocurvature modes can still have strong effects, both in an increase in the power spectrum as well as in the bispectrum. Thank you very much. I hope you enjoyed this video.